this video, we will be approaching a bar problem from Intro to FEA. The nice thing about bars is that you can practically treat them like springs, so the actual math is not as bad, especially if you're familiar with the spring FEA problems. So in our drawing, we can see that we have two bars or two elements that are fixed on both ends. This one is fixed with a pin, and this is fixed as a wall. We're taking both ends as fixed rigidly, which will be applied in our boundary conditions. Other variables we get in the question are the cross-sectional area of element 1, the cross-sectional area of element or bar 2, the value of E, which is our Young's modulus. We can also see an applied force in the center of the first bar, and we get the lengths of each of the elements. Our goal here is to find the nodal displacements, the stresses in each element, and the support reactions. The stresses in each element would be the stress in element 1, the stress in element 2, and support reactions are the reaction force here at this support and the reaction force here at this support, which we can just find using the system of equations that we develop when finding nodal displacements via the global equilibrium matrix. After your givens are clear and you know what you need to find, the next step I like to do is to draw the nodes on my graph and label my elements. Now, intuitively, you might think that we only have 3 nodes, node 1, node 2, node 3, but where the force is applied here in the center of element 1 presents a challenge. Because it's in the center of this bar, what we're going to do is actually make it another node and split the first element into 2 halves. So this end will be our node 1, and then right where the center force is applied will be our node 2. Where the 2 elements touch is our node 3. And on the far right will be our node 4. So we just went from 2 elements to 3 because we split the first bar in half. So I'm going to also label my elements as such. Because we have 4 nodes, our global equilibrium matrix will be a 4x4. Now to start solving, we will do the nodal displacements first. In order to do that, we need our equilibrium equation, which is a very similar process to what is done in springs, where our equilibrium equation will look of the form the stiffness matrix times the displacement vector equal to the force vector, which is just your Hooke's law summation of forces, and usually you'll see it with a little superscript of E, meaning that for each element you can build out this equation and then join them all together to create the overall global equilibrium equation. With some practice, you'll just be able to do that automatically, which is what I will show you. Skip a few steps ahead. So from the amount of nodes that I have, I know that my stiffness matrix is going to be a 4x4 matrix, so I like to add some lines to help me organize it. Now, if you're familiar with springs, our spring stiffness matrix had the form of K minus K minus K, K, where K was our spring constant, or stiffness of the spring. Now, when we're approaching bars, they themselves are treated like springs, but rather than K, their stiffness is defined by the material properties of the bar. So AE over L is placed instead of K for bars, where A is the cross-sectional area of the bar, E is the Young's modulus of the bar, and L is the bar or element's length. So back to the stiffness matrix, I also like to number all the cells like this to help me orient in space. These numbers here are the global node numbers, so 1, 2, 3, and 4, starting with our first element here. This element is the first left half of the first bar, and it's between element 1 and 2. So I'm going to add in this top quadrant of my stiffness matrix A1 L E1 over L1, negative A1 E1 over L1, negative A1 E1 over L1, and A1 E1 over L1. Again, in the same pattern as K, negative K, negative K, K, where you can see the symmetry of that matrix. Now moving on to the second element, this is the right-hand half of the first bar. It's in between node 2 and 3, so if you find 2 and 3, it's going to be in these 4 in the center of the stiffness matrix. So I will change colors. This I will call as, because it's element 2, I named it element 2, A2, E2, L2. So plus A2, E2 over L2 minus A2, E2 over L2 minus A2, E2 over L2 plus A2, E2 over L2. My last element is element 3, or the second bar, and that's between nodes 3 and 4. So in this bottom quadrant, I'm going to put the stiffness coefficients for that second bar, which would be A3E3 over L3 minus A3E3 over L3 minus A3E3 over L3 and A3E3 over L3. Just like that. Every other spot that doesn't have a stiffness variable or coefficient will get 0. As we can see, we have a banded matrix. Next, we can add our displacement vectors, D1, D2, D3, D4. This means the displacements at each of the 4 nodes we have labeled, and that equals to our force vector, which is just our, whoa, that's a crazy bracket, which is just our externally applied forces. Element 1 is fixed on the left. We don't have any externally applied forces, but we call the fixed force a reaction force, so I will put R here. Then at node 2, we do have a force. We have force P, which is 300 kilonewtons in the positive direction, which is the right. So in row 2, I'm going to put P. We do not have any externally applied force at node 3, so this becomes a 0. And then at node 4, no externally applied force, but it is fixed at a wall, and the wall will have a reaction force. So I put R2, and I'll make this R1. Now, thankfully, we can, using the boundary conditions and the fact that there's 2 fixed ends, simplify this matrix and system of equations. We know that because this side of this bar and this side of that bar are fixed at the wall, there will be no displacement at the wall. So that means that displacement at node 1 is 0, and displacement at node 4 is 0. What that means is we can actually eliminate the first row and first column and fourth row and fourth column of this whole system and solve for the 2 unknown displacements at node 2 and 3 using this simplified matrix. So we can actually rewrite our global equilibrium equation to just use this part of the stiffness matrix at displacements of node 2 and 3 and force vector being P and 0. At this point, you can take the given constants from the equation and sub in values, build out your system of equation, and solve for the 2 unknowns, which are D2 and D3. One thing to keep in mind is the units of the givens. So our length units are in millimeters, however our force unit is in kilonewtons, and our E value or Young's modulus value is in newtons per meter squared. So I calculated all my stiffness coefficients using newtons and meters, and I ended up for A1, E1 over L1 getting 3.3 times 10 to the 8. Then for A2, E2, L2, since it has the same area and E value as well as length as the first element or the other half of bar 1, it has the same K constant value. It's the same as A1 times E1 over L1. And then for A3, E3 over L3, this is now bar 2, so I have the area, the E value, and the length, and I get 2.67 times 10 to the 8 Newton meters. Then, given these values, I set it back to my simplified system of equations. I get these coefficients. Now I can actually create 2 equations with my unknowns using this matrix. So using simple matrix multiplication, I multiply this row by this column to get the equation 6.67 times 10 to the 8 d2 minus 3.33 times 10 to the 8 d3 equals 300,000. And why this is 300,000 is because in our image we get our external force at node 2 300 kilonewtons. My units are newtons, so that makes 300,000 newtons. Then for my second equation, I have row 2 of the simplified matrix times the unknowns, so I get negative 3.33 times 10 to the 8 d2 plus 6.0 times 10 to the 8 d3 equal to 0 because there's no external forces at node 3. Then I can rearrange one of these equations to get d2 in terms of d3, where d2 is displacement at node 2, d3 is displacement at node 3. And then I can plug in d2 in the other equation, and I get 3.405 or 3.4 times 10 to the negative 1, 2, 3, 4, negative 4 meters, or 3.4 times 10 to the negative 7 millimeters. Now that I have d3, I can sub it back up here to get d2, so equals 6.2 times 10 to the negative 7 mm for displacement at node 2. Our d1 equals 0, d4 equals 0, d 6.2 times 10 to the negative 7 mm, and d3 equals 3.4 times 10 to the negative 7 mm. I can now use these displacements to compute the element stresses and support reactions. So technically we have 3 elements, half of bar 1, half of bar 2, and full bar 3. So we're going to compute 3 elemental stresses. For element 1, stress is just strain times E, our Young's modulus. Strain is just our change in displacement over the original length of the bar. So in this case, the change in displacement is between nodes 2 and 1 for the left-hand side of bar 1. So strain will be d2 minus d1 divided by L1 times E, d2, 6.2 times 10 to the negative 4 meters, times our E value given from the question, which is 200 times 10 to the 9 Newton meters squared, divided by the length, the half length of bar 1, which is just 0.15 meters. That gives us about 827 megapascals. For the stress in the second element, we do similar. This will be, again, strain times E, our Young's modulus, where strain in this case is the change in displacement between nodes 2 and 3, divided by the length of element 2, which will become d3 minus d2 over L2 times 200 times our E. So that becomes negative 373 megapascals. Notice how the stress in our second half, right-hand half of the first bar is negative. This means that the stress is compressive. This value here, the left-hand half of the first bar, is positive. That means our stress is tensile. The strain in bar 2, or element 3, is just the change in displacement between node 4 and node 3 divided by the length of element 3. So we got d4 minus d3 L3 times E. So we have 0 minus 3.4 times 10 to the negative 7 times 200 times 10 to the 9 Newton meters squared. This is in meters, divided by 0.3, which gives us negative 227 megapascals, which this is negative, telling us that the stress within element 3 is compressive. Due to how you end up rounding your numbers that you use in your stiffness matrix, you might get slightly different values than I did, but ultimately they should round close to what's presented on the board. Last but not least, we want to find the support reactions. So let's go back to our global equilibrium equation. I have just rewritten it on the board. Our support reactions, are the reactions at node 1 and node 4, R1 and R2 respectively. Given that we now know what each of these displacements are, and also that D1 and D4 are 0, We can use the constants and then the solve for displacements to create two equations that allow us to solve for R1 and R2. We're just going to do some basic matrix multiplication to get the equations. So we'll multiply this row by this column. D1 is 0, so I'm not going to add that term. And then our next term would be A1, E1, L1 times D2. And then these are zeros, so that would equal to R1, meaning that our first equation, A1, E1 over L1 times D2 equals R1. Great, and now if we want to find R2, it's a matter of multiplying this row times the displacement column. We have zeros here, so we don't have in our second equation any D1 or D2 terms. We know D4 is 0, so the only term in the equation for solving for R2, our second support reaction at node 4, would just be negative A3 E3 over L3 would just be, negative A3 E3 over L3 times D3 equals to R2. So we can just sub in the values. Just a quick correction regarding the reaction force of node 1. In my stiffness matrix, I forgot the negative sign in row 1, column 2. This term right here should be negative, making the reaction force at node 1 also negative, and after plugging in the numbers rounded, I get negative 207 kilonewtons. For reaction force 2, or the support reaction force at node 4, I get about negative 91 kilonewtons. In summary, that's how you solve this problem for nodal displacements, element stress, and support reactions, with nodal displacements being 0 millimeters for node 1, 6.2 times 10 to the negative 7 millimeters for node 2, 3.4 times 10 to the negative 7 millimeters for node 3, and 0 millimeters for node 4. Element stresses being 827 megapascals for stress in element 1, which is the first left-hand half of bar 1. Stress in element 2 being negative 373 megapascals, that being the right-hand side or second half of bar 1, and then stress in element 3 or bar 2 being negative 227 megapascals. And finally, for support reactions, being the reaction force at the supports, so nodes 1 and node 4. At node 1, about negative 207 kilonewtons, and at node 4, negative 91 kilonewtons. Now these values might slightly vary for you depending on how you round these values and how you compute the stiffness for both of the bars given your givens.